When most people wake up in the morning, they assume they're living in the only world that exists. They brush their teeth, they check their phone, they navigate through their day as if this particular version of reality is the one and only version that matters. But what if I told you that everything you just did, every decision you made, every word you spoke, is happening right now in multiple parallel universes simultaneously? And what if those versions of you are also making different choices, living different lives, in worlds that exist just as real as this one? This isn't science fiction. This isn't philosophical speculation. This is cutting-edge theoretical physics, and it's being taken seriously by some of the brightest minds in the world. Let me introduce you to someone who's devoted his career to understanding the nature of these parallel worlds. Michio Kaku is a theoretical physicist, a futurist, and the author of several groundbreaking books that challenge everything we think we know about reality itself. He's not some fringe scientist working in isolation. He's a respected member of the scientific community who has helped us understand the very fabric of the universe through the lens of string theory, quantum mechanics, and the mathematics that govern our existence. And what Kaku has discovered, what he's patiently explained through equations and evidence and thought experiments, is that our universe might just be one thread in an incomprehensibly vast cosmic tapestry, where infinite versions of reality exist simultaneously, each one as real, as vibrant, and as consequential as the one you're living in right now. The idea of parallel worlds sounds absurd at first. I get it. It challenges our intuition about how the world works. We experience reality as singular, linear, definite. We make a choice, and that choice ripples through our lives. But quantum mechanics has been telling us for nearly a century that reality is far stranger than our everyday experience suggests. And when you combine quantum mechanics with string theory, with the mathematics that describes the fundamental nature of existence, something extraordinary emerges. You're not just one person living one life in one world. You're infinite. Now, before you dismiss this as metaphorical or poetic, let me be clear, Kaku is talking about actual, physical parallel universes where actual, physical versions of you are living actual, physical lives. This isn't theology or philosophy. This is physics. So let's dive in. Let's explore what we know, what we suspect, and what the evidence is telling us about the nature of parallel worlds. Let's understand why one of the smartest physicists alive believes that you, right now, reading this, are living in multiple universes simultaneously. And let's grapple with what that means for everything we thought we knew about existence itself. The story of parallel worlds begins, strangely enough, not with exotic physics, but with a simple problem that physicists discovered in the heart of reality itself. Quantum mechanics doesn't work the way we expect it to. For most of human history, we believed in a universe that operated like a giant machine. Isaac Newton gave us the laws of motion. These laws were deterministic, predictable, and seemingly absolute. If you knew the position and velocity of every particle in the universe, you could, in principle, predict the future perfectly. The universe was like an enormous clockwork, and every moment followed inexorably from the moment before. Then came the 20th century, and everything changed. When physicists began studying the behavior of atoms and subatomic particles, they discovered something that violated every principle of Newtonian physics. These particles didn't behave like objects in the everyday world. They didn't have definite positions until you observed them. They existed in states of probability rather than certainty. And when you weren't looking at them, they seemed to be in multiple places at once. This is the bizarre world of quantum mechanics, and it's one of the most successful theories in the history of science. It's given us transistors, lasers, nuclear energy, and smartphones. Every technology that depends on understanding the behavior of atoms and electrons works because quantum mechanics is correct. But it's also profoundly strange, and it raises questions that physicists have been debating for nearly a century. The most famous of these questions comes from an experiment called the double slit experiment. Imagine you have a source of electrons on one side of a screen. In the screen are two slits. On the other side of the screen is a detector that can register where each electron lands. Now, here's where it gets weird. If you don't observe which slit the electron goes through, it acts like a wave. It goes through both slits simultaneously and interferes with itself, creating a pattern of many hits and few hits on the detector. It's as if the electrons spread out, went through both slits, and recombined on the other side. But if you set up a detector to watch which slit the electron actually goes through, if you force the universe to reveal its choice, then the electron behaves like a particle. It goes through one slit or the other, not both, and it creates a different pattern on the detector. The act of observation changes the behavior of reality itself. This experiment has been performed thousands of times with the same result. It's not a trick or a flaw in the apparatus. It's a fundamental feature of how reality works at the quantum level. For decades, physicists struggled with what this meant. If reality only becomes definite when you observe it, what determines what's real before you observe it? What determines the outcome of a quantum measurement? These aren't peripheral questions. They go to the heart of what reality is. One interpretation of quantum mechanics, developed by physicists like Erwin Schrödinger and Werner Heisenberg, suggested that quantum measurements are fundamentally random. The universe doesn't have a predetermined outcome. Instead, there's a probability distribution of possible outcomes, and when you measure, reality chooses one outcome at random. This idea became the Copenhagen interpretation, and for many years, it was the mainstream view of how quantum mechanics worked. But there's a problem with this interpretation. It's deeply unsatisfying. It says that reality is fundamentally random, that there's no mechanism explaining why one outcome occurs rather than another. It also says that observation affects reality in a strange, non-local way that seems to violate our understanding of how cause and effect work. In the 1950s, a physicist named Hugh Everett proposed a radical alternative. Instead of saying that quantum measurements are random and observation causes the wave function to collapse into one outcome, Everett suggested something different. What if all possible outcomes of a quantum measurement actually happen, just in different parallel worlds? In Everett's interpretation, sometimes called the many worlds interpretation, when a quantum event occurs with multiple possible outcomes, the universe doesn't choose one outcome and discard the others. Instead, the universe splits. For each possible outcome, there's a branch of reality where that outcome occurs. And in each branch, there's a version of you observing that outcome. This is the key insight that leads directly to Michio Kaku's ideas about parallel worlds. If the many worlds interpretation is correct, then every quantum event that has multiple possible outcomes causes reality to branch into multiple versions of itself. And since there are quantum events happening all the time at every level of reality, the universe is constantly splitting into new branches, new parallel worlds. Now let's think about what this means. You're made of atoms. Atoms are quantum systems. Every single atom in your body is subject to quantum mechanics, which means your very existence is the result of countless quantum events. The quantum state of the electrons in your brain, the quantum fluctuations in your DNA, the random quantum processes that occurred during your conception and development, all of these are quantum events with multiple possible outcomes. According to the many worlds interpretation, every one of these events causes reality to split. And in each branch, there's a version of you. In one branch, you made the decision to read the script. In another branch, you didn't. In another branch, you were born at a slightly different time. In another, you were born to different parents. In another, you were never born at all. Michio Kaku takes this idea and extrapolates it to its logical conclusion. You exist across an enormous number of parallel worlds, each one slightly different from the last, each one a variation on the theme of your life. And you're not special. Every conscious being exists across multiple parallel worlds. In fact, Kaku suggests that the number of parallel worlds in which you exist might be in the millions. Think about that for a moment. Right now, at this very instant, there are millions of versions of you living millions of different lives. In one world, you made a choice at breakfast that you didn't make in this world. In another, you took a different job. In another, you met the love of your life. In another, you never did. All of these worlds are equally real, equally valid, equally part of the structure of existence. This is profoundly disorienting when you first encounter it. Our intuition tells us that there's one reality, one timeline, one version of events. We experience consciousness as singular and linear. But quantum mechanics is telling us that consciousness might be a different thing than we assumed. Or perhaps consciousness is always experiencing one branch of reality, but that branch is just one among millions. Now, you might be wondering, if all these parallel worlds exist, why can't we see them? Why can't we interact with other versions of ourselves or other versions of reality? The answer lies in the structure of quantum mechanics itself. When a quantum measurement occurs, when reality branches, the different branches don't interact with each other in any detectable way. They're causally separated. Events in one branch don't affect events in another branch, at least not in any way we can observe. This is crucial. It means that even though all these parallel worlds exist, they're effectively invisible to each other. You can't reach across the quantum divide and touch another version of yourself. You can't receive messages from the alternate world where you made a different choice. Each version of you is isolated in its own branch of reality, but they're real nonetheless. And the mathematics of quantum mechanics tells us they have to be real. The equations don't work if you assume the other branches don't exist. They only work if you accept that all possible outcomes of quantum measurements are real, just in different branches of a multiversal reality. Kaku has spent years developing and refining this picture. He's explored what it means for multiple versions of ourselves to exist simultaneously. He's considered the implications for free will, for destiny, for the nature of identity itself. And he's grounded all of this in the mathematics of quantum mechanics and string theory, which provides an even more elaborate framework for understanding how parallel worlds might exist. So before we go further, let me ask you to suspend your disbelief for a moment. Forget your intuition about how reality should work. Forget the idea that there's one timeline, one you, one version of events. Instead, imagine that you're reading this script, but there's another version of you who didn't read it. There's another version of you who chose to do something else today. There's another version of you who made different choices at every moment of your life, and each one of those versions is living in a real, physical universe. That's the picture of parallel worlds we're developing here. And it gets even more elaborate when we bring in the broader framework of string theory and the very latest ideas about the structure of the cosmos. To understand Michio Kaku's full vision of parallel worlds, we need to zoom out and think about the universe on the very largest scales. Not the quantum scale of atoms and electrons, but the cosmic scale of galaxies and space itself. In the past 2 decades, cosmology, the science of the universe as a whole, has undergone a profound revolution. We've discovered that the universe isn't just bigger than we thought. It's bigger in ways we never even imagined. When we look out at the night sky, we see stars and galaxies extending to the edge of our observable universe. The observable universe is the part of the universe from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. It's a sphere roughly 93 billion light-years across, containing hundreds of billions of galaxies, each with hundreds of billions of stars. That's a staggering amount of stuff. And for a long time, cosmologists assumed that what we could see was essentially all there was. The universe was finite, or at least the universe we could observe and study was the whole universe. But observations from the 1990s onwards have suggested something different. Astronomers discovered that the expansion of the universe is accelerating. This wasn't expected. According to the theory of gravity, the expansion of the universe should be slowing down because gravity pulls everything together. But the data clearly showed that something was pushing the universe apart, making it expand faster and faster. Cosmologists called this mysterious force dark energy. We still don't fully understand what dark energy is, but we know it comprises about 68% of the universe. That's right, most of the universe is something we don't understand. And whatever it is, it's making the universe expand at an accelerating rate. Now, what does this have to do with parallel worlds? Everything, as it turns out. There's a theory in cosmology called cosmic inflation. It was developed by Alan Guth and Andre Linde in the early 1980s, and it's become one of the most important theories in modern cosmology. Inflation says that in the first fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid expansion. Space itself expanded so fast that it doubled in size many, many times in an incomprehensibly brief period. This theory solved several major problems in cosmology. It explained why the universe looks so uniform from place to place. It explained the large-scale structure of the universe. It made predictions that have been confirmed by observations of the cosmic microwave background radiation, the ancient light that's been traveling toward us since shortly after the Big Bang. But here's where it gets interesting for our purposes. Andre Linde developed a version of inflation theory called eternal inflation. In eternal inflation, the universe doesn't just inflate once in the Big Bang and then settle down. Instead, inflation never completely stops. It keeps happening in some regions of space while it settles down in others. Think of it like this: imagine a vast cosmic foam, where different regions are bubbling up from an underlying quantum field. In some bubbles, inflation ends quickly, and the universe cools down, stars and galaxies form, and you get something like our universe. But in other bubbles, inflation continues, creating more bubbles which create more bubbles, in a cascade that goes on forever. Each bubble is a separate universe with its own physical properties. This is the theory of the multiverse, and it's not some wild speculation. It flows naturally from the mathematics of inflation theory. In fact, according to many physicists, eternal inflation is actually the most natural outcome of inflation theory. If you do the math and take it seriously, you get a multiverse. But here's what really connects this to Michio Kaku's ideas. Each of these bubbles, each of these universes, could have slightly different physical properties. The constants of nature, the laws of physics, might vary from bubble to bubble. And if that's the case, then these different universes might support different forms of matter, different kinds of life, different versions of physics itself. Kaku has thought deeply about what this means. If the multiverse is real, if there are countless universes beyond our observable universe, each with its own physical properties, then the question becomes, how do these universes relate to the quantum branching we talked about earlier? This is where string theory enters the picture. String theory is a framework for physics that says the fundamental constituents of reality aren't point-like particles, but tiny, vibrating strings. These strings vibrate in different ways, and different vibrational patterns correspond to different particles, electrons, photons, quarks, and so on. String theory is a radical departure from conventional particle physics, and it's still speculative. We don't have direct experimental evidence for strings, but string theory has several compelling features. It's the best candidate we have for unifying quantum mechanics and gravity into a single coherent framework. And it opens up the possibility of understanding the structure of the multiverse in a deeper way. In string theory, the mathematics suggests that there could be an enormous number of possible universes, each one corresponding to a different configuration of the string vibrations and the geometry of space. Some physicists have estimated that the number of possible universes in the string theory landscape is something like 10 to the power of 500. That's a 1 followed by 500 zeros. To put that in perspective, that's far more than the number of atoms in our observable universe. If the string theory landscape is real, if all these different configurations are actually realized in different universes, then we're looking at an incomprehensibly vast multiverse. And Kaku suggests that some of these universes might be arranged such that they branch off from each other according to quantum mechanics. So now we have two ways of thinking about parallel worlds. First, there's the quantum branching that happens due to measurements and quantum events. Every time a quantum event has multiple possible outcomes, reality branches into different versions. This happens constantly at all scales, which means there's a vast landscape of parallel worlds that are continuously being created through quantum branching. Second, there's the inflationary multiverse of eternally inflating cosmic bubbles. Each bubble is a separate universe, potentially with different physical laws and different properties. And these universes might coexist with the quantum branches, creating an even more elaborate structure of parallel worlds. Kaku suggests that these two pictures might actually be describing the same thing from different perspectives. The quantum branches might be related to or even identical with the branching of universes in the multiverse. When a quantum event occurs, it's not just creating a branch in reality as we experience it. It's creating new universes with different configurations. Now, let's think about what this means for you specifically. If quantum branching is real, and if it's happening at the atomic and molecular level in your brain, then every neural event that has multiple possible outcomes causes your consciousness to branch into multiple parallel universes. Every decision you make, every thought you have, every perception you experience could be a branching point. Consider a simple decision. This morning, you could have had coffee or tea. This is a decision, and before you made it, both outcomes were possible. In quantum mechanical terms, you were in a superposition of states, both coffee drinker and tea drinker simultaneously. When you made the decision and took action according to the many worlds interpretation, reality split. In one branch, you're the person who had coffee. In another branch, you're the person who had tea. Both versions are equally real. But this is just one decision among thousands you make every day. You make decisions about what to eat, where to go, what to say, what to think about. Each decision is a branching point. And if any of these decisions involve quantum processes, and many of them do, deep in the neural machinery of your brain, then each decision causes reality to split. The number of possible worlds created by these branching events is staggering. Kaku suggests that if you could count all the quantum branching events that occur in your brain and body over the course of a day, and then extrapolate over your lifetime, you'd arrive at a number in the millions. That's how many parallel versions of you are living parallel versions of your life right now. This might sound like pure fantasy, but remember, the mathematics demands it. The equations of quantum mechanics don't work if you assume these parallel worlds don't exist. They only work if you accept that all possible outcomes are real, just in different branches of reality. Now, let's dive deeper into the mechanisms that would create these parallel worlds. To understand how you could exist across millions of parallel universes, we need to understand how quantum branching works at the level of your brain and nervous system. Your brain is the most complex object in the known universe. It contains roughly 86 billion neurons, each connected to thousands of other neurons through trillions of synaptic connections. These connections are constantly changing, constantly rewiring themselves based on your experiences and thoughts. Your consciousness, your sense of self, emerges from the coordinated activity of all these neurons firing in patterns of extraordinary complexity. Now, here's the key insight. The neurons in your brain are made of atoms, and atoms are quantum systems. The electrons in your neurons are subject to the laws of quantum mechanics. They exist in probability distributions rather than definite locations. The chemical reactions that occur in your neurons involve quantum tunneling, where particles can mysteriously appear on the other side of barriers they shouldn't be able to cross. For decades, most neuroscientists assumed that quantum effects in the brain were negligible. They thought that the warm, wet environment of the brain would quickly destroy any quantum effects through a process called decoherence. The brain, they assumed, was fundamentally classical. It operated according to the rules of everyday physics, not quantum mechanics. But recent research has challenged this assumption. Some scientists have discovered evidence that quantum effects might play a role in biological processes. Photosynthesis, the process by which plants convert sunlight into chemical energy, seems to involve quantum coherence, particles existing in multiple states simultaneously. Some research suggests that quantum effects might play a role in the sense of smell, in bird navigation, and possibly in other biological processes. The question of whether quantum effects play a role in consciousness itself is highly speculative and controversial. Some physicists and neuroscientists argue that quantum effects in the brain could be relevant to consciousness. Others dismiss this idea as unfounded speculation. But here's what's important. If quantum effects do occur in your brain, if the neural processes that generate consciousness involve quantum events with multiple possible outcomes, then those quantum events would cause reality to branch. Let's think about what happens in your brain right now. As you read this, photons are striking your retinas, triggering chemical cascades in your photoreceptor cells. Electrical signals are traveling along your optic nerves to the visual cortex in the back of your brain. Pattern-matching neural circuits are recognizing words, syntactic structures, semantic meanings. Your attention is being directed to some words and not others. Your emotional centers are responding to certain ideas, creating feelings of interest or skepticism or excitement. All of this is happening through quantum processes. The electrons in your neurons are tunneling, jumping, vibrating. The ions moving across cell membranes are governed by quantum probabilities. The very act of you reading and understanding these words involves countless quantum events. Now, according to quantum mechanics, each of these events could have multiple possible outcomes. Maybe a particular electron tunnels across a barrier, or maybe it doesn't. Maybe a particular ion channel opens, or maybe it remains closed for a few extra microseconds. Each of these quantum events is infinitesimally small, but there are so many of them happening in your brain every single moment that they accumulate. Some of these quantum variations will be noise, irrelevant fluctuations that don't affect your overall experience or behavior. But others might tip the balance. They might cause you to notice something you otherwise wouldn't have noticed. They might cause you to think a thought you otherwise wouldn't have thought. They might cause you to make a decision different from the one you would have made if things had gone slightly differently at the quantum level. And here's the crucial point. When these quantum branching events occur, they cause reality to split. In one branch, you had the quantum fluctuation that made you notice something. In another branch, you didn't notice it. Both versions of you are equally real. Both are conscious. Both are experiencing their own version of reality. Now multiply this across every moment of your existence. Multiply it across the entire history of your life. Multiply it across every possible interaction between your neurons and the quantum processes that underlie them. You arrive at an almost incomprehensibly large number of parallel versions of yourself. Michio Kaku refers to this as the multiverse of you. In this multiverse, there's a version of you for nearly every possible sequence of decisions and experiences that quantum mechanics allows. In one version, you became a doctor. In another, you became an artist. In another, you never went to college. In another, you married your high school sweetheart. In another, you spent your life traveling the world. In another, you never left your hometown. And all of these versions are equally real. They're all you. They're all experiencing consciousness. They're all living their lives in parallel universes that exist simultaneously with this one. Now, this raises a fascinating philosophical question. If all these versions of you exist, which one are you really? Are you the sum of all of them? Are you just one of them? Does the concept of you even make sense anymore? Kaku has thought about this question carefully. He suggests that in a very real sense, you are all of these versions simultaneously. Your identity isn't limited to the particular stream of consciousness you're experiencing right now, in this particular branch of reality. Your identity extends across all the branches where you exist. You are the multiversal sum of all possible versions of yourself that quantum mechanics allows to exist. This is a radical idea, and it challenges our most basic assumptions about personal identity. We think of ourselves as singular beings with a single continuous identity throughout our lives. But if Kaku is right, if parallel worlds are real and you exist across millions of them, then your true identity is far more expansive than you ever imagined. Now, you might be thinking, this is all very interesting in theory, but it's completely untestable. How could we ever know if parallel worlds actually exist if we can't observe them or interact with them? It's a fair question, and it's one that physicists have grappled with seriously. Is the many worlds interpretation of quantum mechanics testable? Is the multiverse testable? Can we ever have any evidence for parallel worlds beyond the mathematical argument that they must exist? The surprising answer is yes, at least in principle. And some physicists have actually proposed experiments that might provide evidence for parallel worlds. One way to think about evidence for parallel worlds comes from quantum interference. Remember the double slit experiment? When electrons go through both slits simultaneously and interfere with themselves, that interference pattern is evidence that the electrons are exploring multiple paths through space. Some physicists have suggested that this interference is actually evidence of quantum branching. The electron is exploring multiple branches of reality. If this is true, then anywhere we see quantum interference in nature, we should see evidence of multiple reality branches. And quantum interference is ubiquitous in nature. It shows up in atoms, in molecules, in crystals, in the behavior of light. Every instance of quantum interference could be interpreted as evidence of parallel worlds branching and rejoining. Another line of evidence comes from the apparent fine-tuning of the physical constants. The universe seems to be exquisitely fine-tuned for the existence of life. The strength of gravity, the strength of the nuclear forces, the mass of elementary particles, all of these seem to have just the right values to allow stars, planets, and ultimately life to form. If you changed any of these constants by even a few %, the universe would be sterile and lifeless. This fine-tuning seems absurdly improbable. It's as if someone deliberately tuned the constants to allow life. But if the multiverse is real, if there are countless universes with different physical constants, then the apparent fine-tuning makes perfect sense. Most universes will be sterile. Life will only emerge in the tiny fraction of universes where the constants happen to fall within a narrow range that permits life. And obviously, we find ourselves in one of those rare universes where life is possible, because we're alive. This is the anthropic principle. We should expect to find ourselves in a universe compatible with our existence, simply because we couldn't exist anywhere else. And if the multiverse is real, the anthropic principle is a powerful explanation for the apparent fine-tuning of our universe. Some physicists have pointed out that the anthropic principle is a bit of a cop-out. It's using the existence of the multiverse to explain observations that we can make in our universe, but we're not directly observing the multiverse itself. So does this really count as evidence? Kaku takes a pragmatic view. He argues that the multiverse, and the parallel worlds it contains, are real even if we can't directly observe them. They're part of the underlying structure of reality, even if that structure is hidden from us. And the patterns we observe in our universe, the fine-tuning of the constants, the quantum interference effects, are consistent with the idea that parallel worlds are real. There's another way to think about evidence for parallel worlds: the evolution of our understanding of scale. Throughout the history of science, we've repeatedly discovered that reality is larger and more elaborate than we previously thought. When the telescope was invented in the early 1600s, we discovered that the sun is surrounded by planets, and that the universe extends far beyond our solar system. We discovered galaxies beyond our galaxy. We discovered that the observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. Each time, reality turned out to be vastly larger than anyone had imagined. The discovery of parallel worlds through quantum mechanics and the multiverse follows this same pattern. It's another revelation that reality is far more elaborate and expansive than our intuition suggests. And Kaku points out that every time we've made these discoveries, they've turned out to be correct, even when they seemed absurd at the time. So while we can't directly observe parallel worlds, the logic of quantum mechanics demands that they exist. And the fact that this idea makes sense mathematically, that it solves problems and raises the possibility of understanding the universe in a deeper way, is itself a kind of evidence. But there's something even more intriguing. Some physicists have proposed specific ways that parallel worlds might interact or have interacted, and these interactions could, in principle, leave traces we could detect. One of the most fascinating ideas about how parallel worlds might interact comes from the concept of quantum decoherence. As we mentioned earlier, quantum systems are fragile. When they interact with their environment, when they're measured or observed, they tend to lose their quantum properties and become classical. This process, called decoherence, is why we don't see quantum superpositions in everyday objects. The environment constantly observes large objects and forces them to behave classically. But decoherence isn't complete. Some quantum coherence can persist even in the presence of environmental interaction. And there's a fascinating idea that these pockets of preserved quantum coherence might allow for limited interaction between parallel worlds. Imagine a scenario where two branches of a quantum system remain slightly entangled, meaning they're still connected at the quantum level even though they've otherwise branched apart. If that's the case, events in one branch might have a tiny influence on the other branch. The effects would be incredibly subtle, almost impossible to detect. But they might not be completely zero. Some physicists have speculated that these interactions between parallel worlds might manifest as quantum fluctuations or exotic phenomena that we haven't yet explained. We observe strange quantum phenomena all the time that seem almost paradoxical, and perhaps some of these could be explained by subtle interactions between branches of reality. Kaku takes this further and suggests that as our technology advances, we might develop better ways to detect these interactions. We might build experiments sensitive enough to measure the infinitesimal influence that parallel worlds have on each other. And if we did, it would provide direct evidence that parallel worlds are real. Another fascinating idea involves the possibility of actually reaching other parallel worlds. This is highly speculative, and most physicists would say it's probably impossible. The quantum divide between branches of reality is absolute. There's no mechanism in known physics that would allow you to tunnel through to another branch. But Kaku has thought about the far future, about what a civilization millions or billions of years advanced might be capable of. He's considered whether advanced civilizations might discover ways to interact with parallel worlds that we currently think are impossible. He's suggested that harnessing the power of parallel worlds might be possible using technologies we can barely imagine. This brings us to one of the most intriguing implications of parallel worlds. If they exist, and if consciousness spans across them, what does that mean for concepts like free will, destiny, and the nature of choice? The philosophical implications of parallel worlds are as profound as the physics. Let's think deeply about what it means that every decision you make causes reality to branch. In your everyday experience, you feel like you make choices. You stand before different options, you weigh them, and you decide. Your choice feels free, contingent, something that could have gone differently. But at the same time, there's an illusion in this experience. Most of your daily choices seem to flow from who you are, from your personality and values and past experiences. If you could somehow go back in time and place yourself in the same situation again, would you make the same choice? Many philosophers and physicists have argued that the answer is yes. They argue that free will is an illusion, that given the same conditions, given the same initial state of your brain and mind, you would always make the same choice. This is the idea of determinism. The future is fully determined by the past, and there's no genuine freedom. But quantum mechanics seems to suggest something different. It says that, at the fundamental level, the universe is not deterministic. It's probabilistic. Before a quantum measurement, there's no fact of the matter about what the outcome will be. The outcome is genuinely undetermined. When the measurement occurs, reality branches into multiple possibilities, all of which are realized. This seems to leave room for genuine freedom, for genuine choice. If every possible outcome of your decision is real, and they're all realized across parallel worlds, then you're free to choose in the sense that multiple outcomes are genuinely possible. But here's the paradox. Even if multiple outcomes are genuinely possible in an abstract sense, that doesn't necessarily give you freedom in the sense we care about. You still only experience one outcome. You still only see one version of the choice being made. In your branch of reality, one outcome occurs and the others don't. So from your subjective perspective, the future is still determined by the present. Kaku has contemplated this paradox. He suggests that the concept of freedom might need to be reconceived in light of parallel worlds. You have freedom in the sense that multiple versions of you are making different choices across parallel worlds. Your true identity, the multiversal you, encompasses all possible versions. So in a deep sense, you are free because all possible versions of freedom are realized. But this kind of freedom is cold comfort when you're experiencing yourself as a singular being making choices in a single timeline. It raises a troubling question. If all possible outcomes of your choices are real, if all versions of you are making all possible choices, then in what sense are you responsible for your choices? This gets at the heart of questions about moral responsibility. We ordinarily think that you're responsible for your choices, that you're praiseworthy for good decisions and blameworthy for bad ones. But if all versions of you exist, and some versions make bad choices while others make good ones, are you responsible for the bad choices if they're happening in parallel worlds you're not aware of? Kaku suggests that we need to think about responsibility differently in light of parallel worlds. Perhaps responsibility extends across all the versions of you that exist. Perhaps the moral weight of your actions is distributed across all the branches in which you exist. Or perhaps morality is local to each branch, and you're only responsible for your actions in the branch you're currently experiencing. These are difficult questions, and they don't have easy answers. But they're questions that physics itself raises when we take parallel worlds seriously. And they suggest that the discovery of parallel worlds, if confirmed, would have profound implications for how we understand ourselves and our relationship to morality and responsibility. There's another philosophical implication that Kaku has explored: the question of identity over time. We normally think of ourselves as persisting as a single entity throughout our lives. You're the same person today as you were yesterday, and you'll be the same person tomorrow. But if reality branches constantly, if new parallel versions of you are continually being created, then in what sense do you persist as a single entity? One answer is that you don't. Your identity is not singular but plural. You're not one person but many, distributed across the parallel worlds you inhabit. Your sense of being a unified self is an illusion created by your consciousness, which only experiences one branch at a time. Another answer is that identity is less fundamental than we usually think. Perhaps what matters isn't that you're the same person from moment to moment, but that there's a causal continuity, that each moment's version of you gives rise to the next moment's version. In a universe with parallel worlds, this causal continuity still holds. Each version of you at one moment gives rise to the next moment's versions through quantum branching. These philosophical questions are fascinating, but they're also deeply unsettling. They suggest that the self, the identity we cling to, might be far more fragile and contingent and plural than we ever imagined. And Kaku has suggested that coming to terms with this truth, really understanding what it means that you exist across millions of parallel worlds, could be transformative for how we see ourselves and our place in the universe. Now let's zoom out and think about what parallel worlds mean for the structure of the universe as a whole. We've been focusing on the quantum branching that creates parallel worlds from microscopic quantum events. But Kaku also discusses the larger-scale structure of the multiverse, the cosmic inflation theory, the landscape of possible universes. In this larger view, parallel worlds might not just be created by quantum branching in your brain and body. They might already exist as separate universes within an eternally inflating cosmic foam. Some of these universes might have different physical laws entirely. Some might have different numbers of dimensions. Some might support forms of matter and life completely different from what we know. Kaku has written extensively about the possibility of exploring this vast multiverse. He's considered what it would mean for humanity to develop the technology to move between universes, to visit other branches of reality, to interact with other versions of ourselves. He talks about this in terms of Type 2 and Type 3 civilizations on his scale of technological advancement. A Type 2 civilization would have the ability to harness the energy of an entire star, and a Type 3 civilization would have the ability to harness the energy of an entire galaxy. If such civilizations exist, Kaku suggests, they might use their vast resources to probe the structure of the multiverse and even to manipulate or traverse between parallel worlds. But here's a sobering thought. If such civilizations are possible, where are they? This is the famous Fermi paradox. If life and intelligence are common in the universe, why haven't we detected any evidence of advanced civilizations? One possible answer involves parallel worlds. Maybe advanced civilizations learn to escape our universe, to migrate to other branches of reality where conditions are more favorable or where they face less competition for resources. Maybe the ancient mysteries and unexplained phenomena we find in the universe are signs of civilizations manipulating reality from parallel universes. This is deeply speculative, and Kaku is careful to note that it's on the frontier of wild speculation. But he explores it as a possibility worth thinking about. The parallel worlds implied by quantum mechanics and cosmic inflation might provide a hiding place for advanced civilizations, a way for them to remain invisible to observers in other universes. Now, there's a different question that Kaku addresses. If parallel worlds are real, what determines which branch you experience? If you're constantly splitting into multiple versions across multiple universes, which version is the real you? Which branch of reality is your reality? The honest answer is, there's no privileged branch. All the branches in which you exist are equally real. The fact that you're experiencing one particular branch is, in a sense, arbitrary. You experience your consciousness through one branch because that's the nature of consciousness. It can only experience one branch at a time. But your true self, your full identity, encompasses all the branches you exist in. This is a strange and disorienting idea. It suggests that your sense of identity, your feeling that you're a singular person with a continuous perspective on reality, is a local effect of consciousness. Your true self is more expansive, more multiform, distributed across the multiverse. Kaku has suggested that understanding this might have psychological and spiritual implications. There are religious and philosophical traditions that suggest the self is illusory, that individual identity is a misconception, and that the true nature of being is more unified and less differentiated than we normally perceive. The idea of parallel worlds, scientifically understood, aligns with some of these traditions. Of course, this is speculative. We don't know if parallel worlds are real. We don't know if consciousness really does span multiple branches of reality. But Kaku argues that the mathematics of quantum mechanics and string theory points in this direction, and that we should take it seriously. let's talk about what we might actually do with the knowledge that parallel worlds exist. If Michio Kaku and other physicists are right, if you really do exist across millions of parallel universes simultaneously, what difference should that make for how you live your life? One immediate implication is a kind of cosmic perspective on decision-making. If every choice you make causes reality to branch, if all possible outcomes of your choices are realized somewhere across the multiverse, then the fear of making the wrong choice might be somewhat alleviated. You can't really choose wrong because all your choices exist somewhere. Every version of every possible choice you could make is happening right now in some parallel world. This might seem like it would lead to paralysis. If all outcomes are equally real anyway, why bother choosing at all? But Kaku suggests it could have the opposite effect. Knowing that all possibilities exist might free you from the burden of trying to choose the one right way forward. You can live your life making choices that feel authentic to you, knowing that in other branches you're making other choices, exploring other paths. There's also a sense in which understanding parallel worlds could increase your sense of cosmic significance. You're not just one person with one life. You're a multiversal being, existing across millions of parallel universes, exploring millions of possible ways of being. Your true identity is vaster and more complex than you ever imagined. Kaku has suggested that this perspective might be valuable for coming to terms with the apparent meaninglessness that can emerge from modern physics. When you learn about the vast scale of the universe, the insignificance of Earth in the cosmic scheme, the brevity of human existence compared to the age of the universe, it can feel demoralizing. You're a tiny speck of matter on a tiny planet orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies in an ordinary universe among possibly infinite other universes. But parallel worlds offer a different perspective. Yes, you're physically tiny, but your identity is vast, distributed across multiple universes, exploring every possible way of being that quantum mechanics allows. In that sense, you're not insignificant. You're a multiversal being, experiencing existence across an enormous number of parallel realities. Another practical implication of parallel worlds comes from thinking about the future. If you could somehow communicate with other versions of yourself in parallel universes, if you could learn what choices other versions of you made and what consequences those choices had, you could learn from their experiences. Imagine if you could peek into the parallel world where you made a different career choice and see how that version of your life turned out. Imagine if you could see the outcomes of different relationship choices across multiple branches of reality. You'd gain invaluable information about how different choices lead to different outcomes. Of course, in reality, we can't do this. The quantum divide between parallel worlds is absolute. We can't communicate across it. We can't access the information about other versions of ourselves. But Kaku suggests that this might be something future civilizations could develop the ability to do. Perhaps sufficiently advanced technology could develop ways to read information from parallel worlds, or even to transfer information or consciousness across the quantum divide. If so, it would open up extraordinary possibilities for learning and growth. There's also a more immediate practical implication. Understanding that quantum effects affect your brain might encourage you to think more carefully about the quantum processes that underlie your mental life. Your thoughts, your emotions, your sense of self. All of these emerge from the physical processes of your brain, and many of those processes involve quantum effects. If you can become more aware of the quantum nature of consciousness, you might be able to work with it more effectively. You might be able to harness the probabilistic nature of quantum processes to expand your creativity, to explore new ways of thinking and being. Some philosophers have speculated that meditation, contemplative practices, and other mental disciplines might work in part by aligning consciousness with the quantum nature of the brain. Kaku doesn't go this far himself, but he does suggest that understanding the quantum and multiversal nature of consciousness could open up new approaches to psychology, neuroscience, and our understanding of the mind. Now, let's address some of the objections and criticisms that have been raised against the idea of parallel worlds. While many physicists take the many worlds interpretation and the multiverse seriously, they're not universally accepted. There are legitimate scientific and philosophical reasons to be skeptical. One major objection comes from philosophers and physicists who question whether entities we can't observe or interact with should be considered part of science at all. The physicist Karl Popper famously argued that for a theory to be scientific, it must be falsifiable. it must be possible, in principle, to prove it wrong. If parallel worlds are unobservable in principle, if we can never interact with them or get information from them, then can the parallel worlds hypothesis even be called scientific? This is a serious objection. It points to a real tension in physics. On one hand, we want our theories to be empirically testable. On the other hand, mathematical consistency and explanatory power are also important virtues of scientific theories. Many physicists argue that the many-worlds interpretation and the multiverse are worth taking seriously precisely because they emerge naturally from the mathematical structure of quantum mechanics and inflation theory. But the objection remains. Are we doing physics, or are we doing metaphysics? Are parallel worlds a scientific hypothesis, or are they more like philosophical speculation? Kaku's response is pragmatic. He argues that we should follow the mathematics wherever it leads. If the mathematics of quantum mechanics and string theory and inflation theory leads us to the conclusion that parallel worlds are real, then we should accept that conclusion even if we can't directly observe the parallel worlds. And he points out that history is full of examples where scientists had to accept the existence of unobservable entities, atoms, electrons, quarks, black holes, dark matter, because the mathematics demanded it. Another objection comes from physicists who argue that the many-worlds interpretation is unnecessary. They say that other interpretations of quantum mechanics, the Copenhagen interpretation or pilot wave theory, or objective collapse theories, can explain quantum phenomena without appealing to parallel worlds. Why introduce all these extra entities if you don't need them? This is a fair point. Occam's razor, the principle that we should prefer simpler explanations, might suggest that we should avoid positing parallel worlds if we can explain quantum phenomena without them. But here's where Kaku's perspective is interesting. He argues that from a certain viewpoint, the many-worlds interpretation is actually the simplest. It doesn't introduce special mechanisms like wave function collapse or hidden variables. It just takes the Schrödinger equation at face value. When a quantum system evolves, it evolves according to the equation, which naturally produces superpositions of states. The many-worlds interpretation says that all of these superposition states are real, existing in parallel branches of reality. From this perspective, it's the other interpretations that are introducing extra complexity. The Copenhagen interpretation has to add a special rule about what happens when you measure a quantum system. The wave function collapses. This collapse process isn't explained by the Schrödinger equation. It's an extra ingredient. Pilot wave theory has to posit hidden variables guiding the particles. Objective collapse theories have to modify the Schrödinger equation itself. So depending on what you consider simple, the many-worlds interpretation might actually be simpler. It's just the Schrödinger equation applied consistently everywhere all the time with no exceptions or special cases. Another objection is more philosophical. Some philosophers argue that the many-worlds interpretation doesn't actually solve the measurement problem in quantum mechanics. It just pushes the problem to a different level. Instead of asking, why do measurements give definite outcomes? You have to ask, why do I experience one branch and not the other? The interpretation replaces one hard question with another equally hard question. This is a legitimate point. The many-worlds interpretation doesn't make the measurement problem disappear. It just reconstructs it as a different problem. The problem of why consciousness experiences one branch of reality rather than another. Kaku has thought about this problem. He acknowledges that it's deep and difficult, but he argues that it's a philosophical problem rather than a physical one. Physics can tell us that all the branches exist and that quantum branching occurs. But why consciousness experiences one branch rather than another is a question that might belong to philosophy, neuroscience, or psychology rather than physics. A third objection comes from the worry that parallel worlds are unfalsifiable and therefore not part of science proper. If we can never observe or test parallel worlds, how can we know they're real? Kaku's response, again, is to follow the mathematics. He argues that the existence of parallel worlds is a logical consequence of quantum mechanics, not an ad hoc hypothesis. And he points out that we regularly accept the existence of entities based on mathematical reasoning rather than direct observation. Black holes were predicted mathematically before being observed, for instance. But he also suggests that parallel worlds might not be completely unobservable. There might be subtle traces of parallel worlds in the structure of the universe. There might be quantum interference effects or anomalies in quantum behavior that could be interpreted as evidence of parallel worlds. And if future physicists develop better theories that make more specific predictions about how parallel worlds interact with our universe, those predictions might be testable. A fourth objection is more radical. Maybe parallel worlds aren't real at all. Maybe they're just a useful mathematical fiction, a way of representing quantum probabilities that doesn't require us to assume that all possible outcomes are actually realized. In this view, parallel worlds are a mathematical tool, not an ontological claim about the structure of reality. Some physicists have made this argument. They say that we can use the mathematics of the many worlds interpretation to make predictions about quantum systems without actually believing that parallel worlds exist. Kaku would likely push back on this. He's a realist about parallel worlds. He believes they're not just a mathematical convenience but an actual feature of reality. The mathematics describes reality accurately, and if the mathematics implies parallel worlds, then parallel worlds are real. This brings us to a fundamental question about how we interpret mathematical theories. Do mathematical structures describe reality as it is, or do they merely represent our models of reality? This is a deep question in the philosophy of science that doesn't have an agreed-upon answer. But most physicists working on quantum mechanics, string theory, and cosmology would agree that mathematics is our best tool for understanding reality. And the mathematics of these fields seems to point toward parallel worlds. So even if there's legitimate philosophical debate about the status of parallel worlds, the mathematical case for their existence is quite strong. Let's now consider what we might call the empirical clues that Kaku and others point to as evidence that parallel worlds might be real, even if we can't directly observe them. The first clue is the success of quantum mechanics itself. Quantum mechanics is the most successful theory in the history of science. It's given us transistors, lasers, nuclear energy, MRI machines, semiconductors, and countless other technologies. It's been tested in experiments millions of times and has never been proven wrong. If a theory is this successful, shouldn't we trust what it's telling us about reality? And what quantum mechanics is telling us, if we take it seriously, is that superposition is real. Before we measure a quantum system, it exists in multiple states simultaneously. The question is, what are these states? Are they just possibilities that only become real when measured? Or are they all real, existing in parallel branches? The many worlds interpretation says they're all real. And if they're real, then parallel worlds are real. The second clue is the apparent fine-tuning of the physical constants and the laws of physics. The universe seems almost absurdly well-suited for the existence of intelligent life. If any of the fundamental constants were even slightly different, atoms wouldn't form, stars wouldn't form, chemistry wouldn't work, and life would be impossible. This fine-tuning might be a cosmic coincidence. It might be due to some principle we don't yet understand. Or it might be explained by the anthropic principle in a universe with many parallel worlds with different physical constants. In a multiverse, most universes will be sterile, but some will, by chance, have the right constants for life. And obviously, we find ourselves in one of these rare universes. This isn't a proof that parallel worlds exist, but it's consistent with the idea. And the fact that a multiverse naturally explains an otherwise mysterious feature of our universe is suggestive. The third clue comes from the structure of quantum entanglement. When two particles are quantum entangled, measuring one particle instantaneously affects the state of the other, even if they're separated by a vast distance. This phenomenon, which Einstein called spooky action at a distance, violated his intuitions about how the world should work. But experiments have confirmed that entanglement is real. Now, entanglement is hard to understand in the Copenhagen interpretation. How can measuring one particle instantly affect another particle far away? But in the many worlds interpretation, entanglement makes more sense. The particles are correlated across all the parallel branches. When you measure one particle, the branches of reality branch further, but the branches of the two particles remain correlated. Again, this isn't proof, but it's a way that the many worlds interpretation provides a more straightforward understanding of a puzzling quantum phenomenon. The fourth clue is the mystery of quantum decoherence. We observe quantum effects in small systems like atoms and molecules, But in larger systems, quantum superpositions seem to disappear. A cat is never in a superposition of alive and dead states. A person is never in a superposition of two positions. Why? The standard answer is decoherence. The interaction with the environment forces large systems to behave classically. But this answer raises new questions. Where does the superposition go? If